Bridget Savitsky, Lab 5, Motion of Falling Objects. Today we'll observe a tennis ball and a paper napkin falling. Our objective was to observe the effects of gravitational force and drag force on these objects following the principle of Newton's second law. The results was that the gravitational force produces an exponential graph and drag force produces a constant slope at a certain point of time when you factor it in. The video of the tennis ball dropping, and this is the y-axis, this is the x-axis. I followed the center of mass of the tennis ball, and it was calibrated according to the radius of the tennis ball. And we can see that as the tennis ball falls, it's accelerating due to gravity, and that's why the distance is becoming greater with each time interval. So it starts from rest, and that's why its initial velocity is 0. It starts at the origin, and I observed it from the instant the ball was dropped to right before it hit the floor. The time interval was around 0.5 seconds, delta t at 0.01. The arrow scales through because of mass, and that would give it a larger gravitational force. We didn't want the arrow to be too big, but not too small either. And this is the progression of how we updated position. Net force is calculated from drag force and gravity being added together, and then that being plugged into the momentum principle to update velocity to ultimately update position. This is the model. As I run it, we can see that because we're only calculating factoring in gravity into the movement of this object, only gravity arrow is going to pop up. And this is what the graph of it looks like, of the actual data versus the model. There's not a whole lot of agreement because of the time step, but the model produces a nice exponential graph going down because there's nothing to counter it, so the object will continue to accelerate as it falls. This model factors in both drag force and gravitational force. We'll run it. So it falls, gravity acts on it, but we don't see the arrow of drag force popping up because there's not enough time for it to come up. And that is shown also in the graph. Right here, this is the model, but what we can see is that it starts to get a more constant slope than before, because that drag force is, even though it's very small that it didn't show up in the model, it's actually still countering the gravitational force, and there's not a lot of agreement still because of the time step, but I would say it's a more accurate depiction of what actually happened. Let's look at the napkin now. It's going to fall, but not in a straight line. See? This is the y-axis and this is the x-axis. I calibrated the screen accordingly. Look at the model for the napkin falling. The initial position is right below the origin. Its velocity is at 0 because it starts from rest. I observe it from the instant the napkin was dropped to right before it hit the floor. Time interval was about 1.3 seconds, delta t at 0.01 for precision. The arrow scale is 400 because it's a very small mass. And the same position update is going on in the code. That net force is calculated by sum of drag force and gravitational force, momentum principle to update velocity, and then finally the position update. Here's the code of gravity only. So it's predicted that the napkin's just going to fall straight down, no drag forces showing up here. And this is the plot of the model versus what actually happened. There's not any agreement at all, and that's obvious because there's so much drag going on in the actual model. This is actually factoring in drag and gravitational force. As predicted, it's going to fall, but the drag force is going to counter it going upward, and it's going to eventually, it's modeled to reach a terminal velocity. We can see this in the graph. Still not a lot of agreement, but it's because the model didn't account for the side-to-side motion that we saw in the video, and this means that the y values would change extremely slowly in what actually happened. But we can still see that it's predicted that if it did fall in a straight line, it would eventually reach a terminal velocity. What does this all mean? So we can see from the models and the actual data that when you drop an object, it will increase its velocity because of the acceleration due to gravity, but it has that air resistance on it pushing upward, and so eventually it will cancel out and the net force will be 0, making it go at a terminal velocity or a constant velocity. So we expect the models with both gravitational and drag force to be the models that predict terminal velocity, and in fact, we just saw that they do. From this, it's important to note that the drag force opposes velocity and not gravity, and we can also know that when we have drag and gravitational force factored into these equations, the net force will reach zero, and when gravity only is factored in, the net force will continue to increase, and that's why the function is exponential. And finally, we can also see that the momentum principle and Newton's second law is used in these models. So what if the napkin fell with an initial velocity? Well, let's say it's falling at 0.64 meters per second downward. For gravity only, after plugging this into the initial condition in the model, this is the graph that was shown. The blue is the new model, the red is the old model. Both have nice exponential curves, which makes sense because they're accelerating downward. There's no drag force to counter the velocity. And also we can see that the new model, the napkin that has an initial velocity, is going at a farther distance than the one that doesn't have it, and that makes a lot of sense because it isn't just starting at zero. And we can also see this in the graph that calculated drag in it too. So I estimated drag to be around 0.3 meters per second for this model. After plugging that in, we can see that it will reach a terminal velocity with that constant slope, but shows the same thing still, that it will go a farther distance than if it had just started at zero. You can ultimately see from this that the forces will eventually be equal and opposite, cancel each other out, and so the models that produce this terminal velocity are the ones that factor in both gravitational and drag force.